Okay, I would like us to finish up section 4.7 in this video. We're talking about optimization problems, and we only have one more problem left on this worksheet here. So let's get right to it. Let's take a look at problem 8. Part A, okay, it says a small island is 1 mile from the nearest point P on the straight shoreline of a large lake. If a woman on the island can row a boat 3 miles per hour and can walk 4 miles per hour, where should the boat land in order to arrive at a town that is 10 miles down the shore from point P in the least amount of time? All right, so I've got a picture. Here's an island that is 1 mile from the nearest point on the mainland, which we're calling point P. Point P is 10 miles down the road from a town. Okay, and so I've got that distance indicated there. And let me call the, so she's, there's a woman in a boat that's going to land somewhere between point P and where the town is located. We'd like to figure out where exactly should she land so that the distance, the time that it takes her to get from the island to the town is as small as it can possibly be. Okay, now she can row a boat 3 miles per hour. She can walk at 4 miles per hour. Okay, so how, where should she land the boat? Well, let me call the distance from where she lands the boat to point P X. The town is 10 miles away from point P. So if that distance from where she lands the boat to point P is X, then the remaining distance that she would have to walk to town would be 10 minus X, right? Because 10 minus X plus X would give me 10 miles there as that distance. Now, in this picture, I've got a right triangle, and so I can use the Pythagorean theorem, okay? The distance that she would have to row the boat is going to be the hypotenuse of this right triangle. Okay, x squared plus 1 squared equals the hypotenuse squared. That means the hypotenuse would be the square root of x squared plus 1. Now, in this problem, we're going to need to use the formula distance equal rate times time, but when that equation has been solved for time. Okay, since we would like to know where should she land the boat in order to have the time that it would take her to row and then walk to town be as least as it possibly can be. She wants to get there in the least amount of time. Okay, well, I'm going to call this function f of x that we'll be minimizing. We want to minimize the time, and I'll be using this formula here, distance equal rate times time, but when it has been solved for t. Now, the distance that she is going to row the boat is the square root of x squared plus 1. So that would be d. And she can row a boat at 3 miles per hour. Okay, so 3 would go in the denominator. Whatever that time is, I would then add the time that it's going to take for her to walk the rest of the way to town. The distance that she'd be walking is 10 minus x, and she can walk at a rate of 4 miles per hour. So 4 would go in the denominator. This is the function then that I would be working with. And I want to minimize this function, which is a function of time. Okay. What do we know about x? Well, x has to be between 0 and 10. Okay, point P is 10 miles away from the town. Now, if x is 0, that would mean that she's going to row the boat directly to point P and she's going to walk 10 miles to town. She could do that. If x is 10, then that would mean that she's just going to row the boat from the island straight to town. She could do that. X is not going to be outside of these boundaries, though. Okay, but you'll notice that we've created a closed interval here in this problem. So in order to minimize this function, we're going to be using techniques from section 4.1. Okay, I'd like to know the absolute min on the graph of f of x. Well, let's get our critical numbers. and then we'll plug in the critical numbers along with the two endpoints, and we'll see which one is the smallest output there. Okay, so let me do that. We've got 10 over 4, derivative of a constant is always 0, right? The derivative of negative 1/4 x would be negative 1/4, and then plus 1/3 is a constant, right? So then the derivative of the square root of x squared plus 1, that'd be a chain rule. You're going to have 1/2 times x squared plus 1 to the negative 1/2 times the derivative of x squared plus 1, that's 2x. The 2's will cancel, and x is still going to remain in the numerator. I've written this in a radical form here. And, okay, I'm going to set this equal to 0 since I want to find the critical values. Let's add 1/4 to both sides. And then I'm going to cross multiply this here. So let's multiply by 3 times the square root of x squared plus 1, and then multiply by 4 to get to this next line. And you can square both sides to get rid of the radical there. 16x squared equal 3 squared is 9 times the square the square root of x squared plus 1 squared would be x squared plus 1. Distribute the 9, and then 16x squared minus 9x squared would be 7x squared equal 9. Divide by 7. So x squared would be 9 over 7. And if x squared equals 9 over 7, and you take the square root of both sides, x would be plus or minus 3 over root 7. Now, x can't be a negative, right? So throw away the negative there. But 3 over root 7 would be my one and only critical number then. So let's go ahead and plug in the critical number along with the two endpoints here on the interval. We'll see which one is the smallest. Well, if x is 0, then you're going to have 10 over 4 plus 1/3, which would give you 17 over 6, or roughly 2.8 hours is the output there. Okay, and that would be if she were to just row straight to point P and then walk 10 miles. Okay, it's going to take her 2.8 hours. If x is 10, we plug that in. Here's this term is going to go to 0. You're going to have the square root of 101 divided by 3, which would be roughly 3.3 hours. Okay, so if she were to row the boat directly from the island to the town, it would take her 3.3 hours. If x is 3 over root 7, and you plug that into the function, I was getting roughly 2.7 hours. Okay, so that output was the smallest out of these three. Therefore, she should land the boat 3 over root 7, which is roughly 1.13 miles down the shore from point P. Okay, she'd want to land the boat 1.13 miles and then walk the rest of the way. If she goes with any other plan, it's going to take her more than 2.7 hours then. So, okay, how about part B? Suppose that the woman uses a motorboat that goes 20 miles per hour. Where should she land? Well, the only adjustment here in the function from what we had earlier is the rate of the motorboat versus the rate at which she's in a rowboat. Okay, so I've just changed this 3 to a 20. The conditions on X are still going to be the same, right? Point P is 10 miles away from the town. And so let's go ahead and find our critical numbers here. I've got my closed interval. F prime of X would be negative 1/4 plus X over 20 times the square root of X squared plus 1. Basically, you'll have a similar deal here, only a 3 was replaced by a 20. Okay, so 3 is replaced by a 20, right? And when you square both sides, 20 squared is 400. And 16x squared minus 400x squared would be negative 384x squared equals 400. If you divide both sides by negative 384, then x squared would be 400 over negative 384. Now, there's no real solutions to that equation, right? When you square a number, you'll never get a negative. So, there are no critical values on this interval, which means that all we need to do now is plug in the two endpoints and see which one is going to be the smallest output. Well, let me do that. So if x is 0, you're going to have 10 over 4 plus 1 over 20 is 51 over 20, or that would be 2.55 hours. That's an exact, by the way, so I didn't need any approximation sign there. And how about if x is 10? Well, this term is going to go to 0. And this term here, you're going to have the square root of 101 over 20, which would be roughly 0.5 if you go nearest one digit. She should land the boat at the town. It's only going to take her a half hour. By the way, I think that, early on, hopefully we notice that, hey, if she's in a motorboat now going 20 miles per hour, she's going to want to take the boat straight to the town. She's not going to want to walk, right? She's not going to want to take a rowboat, right? Take the speedboat all the way. She can get there in a half hour, okay? All right, so that is all I had then for this section. I mentioned the things that I'm looking for when I grade problems in this section, okay, on a quiz or a test. I'll just kind of go through that again. So when you're working through a problem here, here's what I'm looking for. I'm looking for the function, whatever it is, make sure that that is written, and then make sure that you describe the conditions on x. If those conditions are not written, you won't get full credit. The conditions on x tell us if we're going to use the methods in section 4.1 or 4.3. If we have a closed interval, we're going to be using 4.1. We just get our, like we did here, we just get our critical numbers, plug in the critical numbers along with the two endpoints and see which output is the biggest or the smallest. Otherwise, if we're using an open interval, like was the case here in like problem 5, for example, we are not using techniques from section 4.1, but rather techniques from section 4.3. You need to find your critical numbers, and then you need to prove that that critical number produced an absolute max or an absolute min. Okay, you can use the first derivative test or the second derivative test. I don't care which one. Just make sure that you've used either one of those tests, okay? Because that is the proof, showing that you indeed got the correct value there that would give a min or a max. Okay, and then of course make sure that you got the answer, whatever it is. Make sure that the answer is circled. Okay. Also, of course, make sure that the units are there in the answer, whatever they are, stated in the problem. Okay, so that is what I'm looking for when I grade your work. Of course, a picture is helpful. Okay. I would encourage you to draw a picture. And on some of these problems, there's already going to be a picture there. On some of them there won't be, but a picture I believe is helpful in getting set up correctly, and so consider that. All right, here's the homework on page 337. We are not going to cover section 4.8. 4.9 I'm going to cover in the next video. That's the last section in chapter 4.